Hello everyone, welcome to my presentation. My name is Shuoguang and I'm an assistant professor in Hong Kong University of Science and Technology. Today I'm going to present my work, Revenue Maximization and Learning in Products Ranking. This is a joint work with Ningyuan Chen from University of Toronto and Anran Li from LSE. In this work, we focus on the revenue maximization for online retailers. To start with, we consider a case where a consumer would like to purchase items in online platforms. Suppose a consumer wants to purchase a keyboard. She would like to search the keyword keyboard in the online platform, and the platform would display a few related products of different prices, brands, and qualities. To obtain better knowledge of the display products, the consumer would click one of them, read the detailed description, and make the decision to purchase or not. People may wonder how consumers would behave in this process. Some experiments have been conducted in the literatures. First of all, when making online purchases, consumers usually have limited attention. Experiments show that users are less likely to examine the results near the bottom. Secondly, consumers would purchase an item that is satisfactory rather than keep seeking the one that maximizes her utility. Thirdly, in search engines, experiments also show that the number of clicks received at the top positions are much higher than those at the bottom. The above experiments give us important guidance to model consumers' behavior when making online orders. Then, there are a few research questions to answer. As an online retailer, knowing a consumer's preference, which set of products should be displayed to the consumer, and in what order should the products be placed. Meanwhile, when the consumer's preference towards the products are unknown, can we design a personalized online learning algorithm that achieves good performance? Before presenting the detailed work, let me first have a brief review about the related works. Our problem is related to the choice models and assortment planning. Meanwhile, in the online setting, it is also related to online learning and product recommendation and the multi-abundance framework. Let's begin the major part of this presentation. We first introduce some notation which are used throughout this presentation. We consider an environment where there are n candidate products available to be displayed in at most m slots. We denote a ranking by sigma, and we use sigma I to represent the item displayed at the ith position of this ranking. Given a product is viewed by customer, we denote the conditional purchase probability by lambda I. Therefore, the conditional purchase probability of products displayed at the ith position of sigma is represented as lambda sigma I. Furthermore, we consider a case where consumers' attention span is random and unknown and denoted by x. We use gx to represent the probability that the attention span equals x, and capital Gx to represent the probability that the attention span is at least x. Let us first study the purchasing behavior of consumers. Suppose a consumer is viewing a list of 5 items, 1, 3, 5, 7, 8, with the attention span being 4. In particular, product 1 is displayed at the top, product 3 is displayed at the second position, and so on. The consumer would view this product sequentially and will view at most 4 products. After viewing product 1, there is a probability lambda sigma 1 that the consumer is satisfied. In this case, she will purchase this product and leave the system. If not, she will then view item 3, which is displayed at the second position. There is a probability sigma 3 that the consumer is satisfied with item 3. Consequently, we can say that the probability of consumer purchasing item 3 is 1 minus lambda sigma 1 times lambda sigma 2. Continuing this process, the consumer would keep viewing the products and purchase the one that makes her satisfied. She will leave the system after viewing the 4th product if nothing makes her satisfied. After studying consumers' purchasing behavior, we then mathematically introduce a product ranking problem. We let Rj be the revenue obtained by selling product J. Under our model, the expected revenue obtained from a consumer with fixed attention span X and the display sigma is R sigma X. As we consider the case where consumers have random attention span, the total expected revenue obtained in this case is expectation of R sigma X, where the expectation is taken over the random attention span. As a consequence, the retailer's problem is to find the optimal display that maximizes the total expected revenue under a cardinality constraint that there are at most n products to be displayed. Then, let me briefly compare our model with existing ones. Our model differs with existing models in the following perspectives. First of all, our model aims at maximizing the revenue instead of clicking probability. In the case of maximizing clicking probability, the optimal solution can be obtained by selecting the ones with highest clicking probabilities. However, things are more complicated in our model because the revenue is also involved. Secondly, our model considers a random attention span instead of fixed ones. The optimal ranking and the fixed attention span can be solved by dynamical programming, where there's no clear path to find the optimal solution and the random attention span. As we have mentioned, our problem is more difficult to solve than existing ones. Let me provide a motivating example to illustrate the hardness. Consider the case where the online retailer is able to display 2 out of 3 products. The probability that the consumer would purchase items 1, 2, 3 are 1, 0.1, and 0.52 respectively. The revenue incurred by selling these products are 100, 900, and 190 respectively. We first consider a case when all the customers have fixed attention span x equals 1. In this case, the optimal display is to put product 1 in the first position, with revenue being 100. Then, when all consumers have attention span x equals 2, the optimal display is to put product 2 in the first position, and put product 1 in the second position. As we know the consumer's attention span is 2, the revenue is 180 based on our previous formulation. However, when the consumer's attention span is random following this distribution, things are more complicated. In fact, the optimal display would be put product 3 in the first position and put product 1 in the second position. The corresponding revenue of this display taken over the random attention span is 103.6. Then, let's take a look at the optimal ranking obtained for distinct scenarios. We can see that the optimal display for random attention span, which is to put product 3 in the first position and put product 1 in the second position, is not guaranteed to have any relationship with those optimal displays and fixed attention spans. Then, solving the optimal ranking and fixed attention span does not directly give us any intuition to obtain the optimal ranking and the random attention span. It requires unique treatment to consider the random attention span problem. Before going into details, in this work, we index the products in the order of decreasing revenues for ease of notation. Our first surprising result in this work is that the optimal ranking and the different attention spans have a nested structure such that sigma 1 is a subset of sigma 2, and sigma 2 is a subset of sigma 3. In particular, the products within the optimal ranking under attention span k are contained in the optimal ranking under attention span k plus 1. Using this nested structure, the optimal ranking and the fixed attention spans could be easily solved by dynamical programming. We present a rank optimization algorithm to efficiently solve the optimal rankings for each different fixed attention span. Then, the nested structure looks a little bit abstract to understand. Let me provide an example for illustration. Suppose a retailer wants to display 10 products over 5 slots. The optimal ranking are as follows: sigma 1 equals 3, sigma 2 equals 3, 8, and so on. The next result says that every product contained in the optimal ranking and the fixed attention span k must also be contained in the ranking and the fixed attention span k plus 1. So let's take a look at the optimal ranking and the attention spans 3 and 4. We observe that all items in sigma 3 are also contained in sigma 4, and all items in sigma 4 are also contained in sigma 5. This is a nested structure. Meanwhile, it's worth mentioning that the relative order for the products and the different attention spans are also preserved. For example, product 3 is on the top of product 8 in sigma 3. Then, in sigma 4 and 5, product 3 should also be placed on the top of sigma 8. Using this property, with further analysis, we develop an algorithm that finds an approximation solution being 1/e of the optimal. Our algorithm finds a path to solve the random attention span from fixed attention span solutions. Briefly speaking, we first solve the random attention we first solve the optimal rankings for each fixed attention span. Then, among all these rankings, we find the one that maximizes the term R sigma xx times the tail probability capital Gx. Intuitively, the capital Gx is the probability that the customer will view at least X products. So this term is a lower bound of the revenue obtained by using sigma x as a display, and finding the sigma such that this term is maximized can be equivalently viewed as finding the ranking such that the lower bound of them is maximized. With further analysis, we prove that the obtained lower bound is at least 1/e of the optimal for all attention span following increasing failure rate distribution. This implies that our algorithm is guaranteed to find a 1/e approximation solution to the true optimal. So far, we have studied the offline products ranking problem and developed a 1/e approximation algorithm. In real world, the consumer's preferences towards products and the consumer's attention span distributions is usually unknown. To overcome this issue, we develop an online learning algorithm which learns consumers' characteristics and recommend products to consumers. In our online learning part, we consider a setting where T consumers arrive sequentially. We assume that the consumer shares a common distribution of the attention span. Then, in most existing works, consumers are assumed to have the same preferences towards products, so only the features of products are required to be considered. In our model, we also take the consumer's features into account. To be specific, we use YT to represent the feature of consumer T, and use ST to represent the feature of we use SJ to represent the feature of product J. We assume the probability of consumer T purchasing product J follows a linear form, lambda Tj equals S times theta times Y, where theta is an unknown parameter to be learned. Then, by taking the inner product of S and Y and vectorizing it, this probability can be equivalently viewed as X Tj times theta star, where XTj is a vectorization of the outer product of S and Y, and the theta star is also a vectorized form of the original capital theta star. Here, since our offline algorithm is only able to find 1/e approximation solutions, when defining the regret, we compare the performance of our offline algorithm against 1 over E of the true optimal. Then, borrowing the idea of UCB algorithms, we develop an online learning algorithm, rank UCB, that constructs optimistic estimators of consumers' choice probabilities and attention spans in each round, and make recommendations for consumers. In particular, in each learning round, the parameter theta and hazard rate h are first estimated by ordinary least square. Then we add a penalty to these ordinary least square estimators for both the purchasing probability and hazard rate, and construct their optimistic estimators. Next, we adopt these optimistic estimators as a true parameter and compute an offline solution theta to be displayed to the customer. We then observe the customer's feedback and update the belief of the parameters in the subsequent round. This is the main structure of our online learning algorithm. Next, we prove that the cumulative regret incurred by our algorithm is bounded in the order of square root of t, which matches the regret result in most classical cascading bandit models with fixed attention span and uniform prices. Meanwhile, recall that we only have an 1 over E offline approximation oracle. If we ignore the computational efforts and explicitly solve the offline problem in each round, our online algorithm is also able to achieve the similar regret in the order of square root of t. To conclude, in this work, we first propose a model that extends the well-known cascade model in 2 dimensions, random attention span and different prices. We develop an offline algorithm with 1 over E performance guarantee for the optimal ranking problem. And then in the online learning framework, we also develop an online algorithm, rank UCB, that achieves square root of t regret when the parameters are unknown. That's all for my presentation. Thanks for attending my presentation.